So this workshop is held by Vatsalya. He is the data science head. I am the data science event head under the Cyber Club. Sparsh is the Cyber Club head. Okay, so this workshop is an introduction to, as the slide suggests, ML, AI, and DL, which stand for Machine Learning, Artificial Intelligence, and Deep Learning. So throughout the presentation, we'll be using these short forms, shorthand for these. So whenever we say ML, we mean machine learning. When we say AI, we mean artificial intelligence. And when we say DL, we mean deep learning. So just by a show of hands, how many people are familiar with these concepts? Okay, so we have a mixed crowd. So I'm sure everybody's heard of these terms before. You may not know what they are exactly, but let's start with an agenda of what we have planned for this workshop. Let's aim to keep it about an hour and 15 minutes. So it will be fairly quick, fairly brief. So this is our plan for this workshop, just talking about artificial intelligence, machine learning, and then some implementations of something you can relate to with how ML and AI is used in our day-to-day lives, and some fundamentals of ML. So this is somewhat deep, but we'll just glance over them. So maybe just give you a quick brief on what ML has to offer. And then we'll go over to show you a workflow of how ML works, and then end off with just a brief, like a dip into what neural networks are and what they can do. Okay. So artificial intelligence. Everybody's heard of artificial intelligence. The biggest thing now is ChatGPT, DeepSeek. So what is artificial intelligence? Right. Okay. So by definition, IBM says that artificial intelligence is a technology that enables computers and machines to simulate human learning, whatever. So artificial intelligence as a whole is programming machines in a way where they're able to simulate or try to simulate human behavior or human language or some form of human trait where we're able to give a machine something and expect a response like we would expect a response from another human. That's artificial intelligence. And if you look at this graphic, you can see the hierarchical structure of how everything we will talk about today and what we're not talking about today is structured. So artificial intelligence is the big thing. Under that comes machine learning, and then comes deep learning, and then generative AI. So generative AI is pretty new. Gen AI takes into account all your GPTs and all your image generation, audio generation, all of that stuff. Okay, so a brief overview of artificial intelligence. Now let's go to ML. So machine learning, as shown in the graphic, comes under artificial intelligence. What machine learning does is, as it defines itself, it's a subpart of artificial intelligence which focuses on being able to be autonomous, being able to have a set of training data and being able to predict or to perform with some level of accuracy where we're able to teach it something. So, for example, if you're able to teach somebody a concept and then give them a quiz, a person will be able to answer questions regarding that quiz or that concept. That's practically ML. Now ML, there's not too much to talk about ML, but some real world examples that you can relate to for artificial intelligence and ML is facial recognition, your ERP system. The ERP system works on both machine learning and AI, so AI but machine learning within. So how a brief overview of how facial recognition works is every time it looks at your face, it takes a picture and it adds it to the database under your name. And so when it takes enough pictures, it's able to learn what your face looks like in different lightings, different environments, all of that. Now chatbots, I don't think I have to explain. ChatGPT, DeepSeek, all your black box AI. All these chatbots use AI machine learning to be able to. Yes.
What about the chatbots in Swiggy and Google website? Are they all AI?
Yes, they're all AI. So they're all running LLMs, large language models, which then get integrated into AI. Image generation, as I talked about, is AI. That comes under Gen AI. And regression. Regression is ML. We will talk about regression later. There's multiple types of regression. One we will discuss later is linear regression, which is taking a data set and finding a linear correlation between the X and Y. Okay, let's move on. So let's talk about some fundamentals of machine learning. What builds machine learning as a concept and what we do with machine learning. So there's three major ones, two major ones, one extra one that we'll just brief over and you can read up on it if you want. So supervised learning. How many of you have heard of supervised learning? Okay. So supervised learning as itself is, okay, let's take an analogy. Let's look at a baby. okay, and you have shapes, and you want the baby to be able to figure out which shape goes where. There's two ways you can do it. One way is supervised learning, where let's say the baby points to a shape and you say, okay, that's a square. Now you tell it what the shapes are, you label the shapes, and then in the exam that you're giving the baby, quizzing the baby with the shapes, the baby knows what is what. And so if the baby is smart enough, he'll be able to use those labels and give you with some level of precision an outcome where it's able to segregate your data, squares and triangles. So the main difference you'll notice between supervised and unsupervised learning is labeling the data. So here data is labeled, where you're passing labels in hexagon, triangles and squares. Now if you go to unsupervised learning, you'll see that there's no labeling step. You have unlabeled data and you're asking the algorithm to figure out some correlation between squares and triangles and circles. So here you can see this squares, triangles and circles. Now you're asking the algorithm to figure out why these squares and circles are different, or why triangles and squares are different, or what separates them. And so of course unsupervised learning may not be as precise initially as supervised learning because there's no labeling of data. It doesn't know exactly what it's looking for, but it's trying to predict what the similarities between certain things are. For example, it can look at volume. If they're all similarly shaped, you can say, okay, the volume of the square is something. If you look at the sides and the area, it can figure out some correlation between all of them together and segregate. That's unsupervised learning. Now another form of learning that you'll see a lot, or not as much, is reinforced learning. So reinforcement learning is something that us humans have a lot that we don't realize is being used with us. Reinforcement learning is you're given some data, you run it through a model, and if the model gives you a desired output, you give it a reward. It's the same case as with children to some extent. Is you ask them to do something, and then if they do something right, you give them a reward for it, and so you're training it or incentivizing it to do the right thing to some extent, or get correct answers or answers you're desiring, and you're also incentivizing it to not get it wrong.
So it's like you see how you give things to ChatGPT, it gives you a result. Sometimes it'll be like a thumbs up and a thumbs down option. Is that reinforcement learning?
No. So with ChatGPT, when you give a thumbs up or thumbs down, that's just a review.
Okay.
So all that is doing is it's just giving OpenAI, the parent company, it's just giving the prompt and saying, okay, this wasn't right. So then OpenAI does something about it. ChatGPT does it.
Oh.
So reinforcement learning with Chat, you can try and train ChatGPT on reinforcement learning by saying, okay, give me this prompt, and say, no, you're wrong, and then give it something else.
Okay, so if you like directly input the data that is wrong, this is what. This
Yeah,
is
so
what
you can incentivize it to give you the right answer, saying, okay, this is wrong and this is right, so you follow this thread.
So that is reinforcement learning.
To some extent, you're forcing reinforcement learning on ChatGPT.
Okay.
But ideally, how reinforcement learning is, you have an algorithm and you have some data, and you create a script that will go through the data, pass the inputs to the algorithm, and the algorithm will give you some output. But you know what the output should be. And so, depending on the relation between what it gave you and what the output should be, you're able to give it some reward. Or some, yeah, so usually how it works is you have a binary or a value between 0 and 1. 1 being highest reward, 0 being no reward. And so the closer it is to 1, the better. So it tries to reach 1. So yes.
So now that we know what ML is, do you have any questions? You can shoot if you have any questions. Because now we're going to delve deeper into not too technical, but a more application-based approach where we learn how to execute a ML model from scratch. And it is going to be slightly theoretical. You might encounter things which you already know, but I think it's important to go over the basics. So this is a very drone shot view of how to execute a pipeline in machine learning. So obviously you have to get it. I can even switch the next slide. This is a more detailed view, and I think we're going to follow this process particularly. So it starts with problem formulation, where you obviously, with respect to the stakeholders for which you try to solve the problem for, you define the problem very clearly, and obviously for that problem you acquire the data, you will have to go through the processing, and finally you train the model, you evaluate the model, do some fine tuning, and finally deploy the model. So we're sort of going to delve deeper into each part, the theoretical aspect of it. So yeah. So problem definition is, I think, very crucial when you start with an ML problem. So if you so essentially you have to have a structured game plan from the start. So if you want to execute an ML model, you have to have a clear problem in your mind. So the problem has to be as objective as it can get, because, for example, if you're trying to predict the sales in ML, that's a very vague statement. Rather, you would say that I want to predict the churn in the customers for the next 3 months. So it's a more theoretical. It's a more theoretical problem and not vague. So you know what you're working for. And obviously, you need to talk to the stakeholders as well, because you need to understand the problem well, that what actually do you want to predict. Do you want to predict it for the future, or do you want to predict the trends which are already there? Then you'll have to measure, somehow find some way to measure the prediction, which will come under model evaluation. Yeah, you can switch over the next slide. So yeah, next process is data collection. So once you've identified your problem well, the next key part is obviously collecting the data. So you will have to figure out, in real world examples, it's not easy to fetch data, and you will have to figure out your own ways and your own creative ways to fetch the data from. You will have to make sure that the data is relevant for your problem. So for example, as I said about a churn prediction problem, you might want data which has previous history of customers who have their purchase patterns, probably their spending patterns, their customer support records, etc. etc. We'll have to ensure that you have enough examples, because all the machine learning models, for deep neural networks, it's even worse. Like, you have to have a lot of data, but you have to have sufficient data, and it has to be a balanced segregation. So for example, if you're doing for a churn prediction model, it's a classification based problem where you have two targets: either the customer has churn or they have stayed. So you will have to have a balanced set. You can't have a data set which will have only 10% of churn customers and rest 90% of the customers who have stayed there. So you need to have, and the quality of the data matters. Obviously, you have to make sure that you fetch the data from the right sources. You have to check if the data is accurate, up to date, and if it's legally or ethically useful. I will just briefly go upon the very common ways of fetching the data from. So have you guys gone through Kaggle anywhere? Just raise your hand. So Kaggle has a ton of public data sets. You can just download the data set, do your machine learning model. That's one way of dealing with it. You can just take public data sets and work your problem through. The second option is APIs. So I don't know if you guys have heard that Twitter, Instagram, all of these platforms offer APIs to fetch the data from. So for example, Twitter has an API to fetch the tweets from. And if you're working in a closed source problem, then you might have a database. Like you might have a structured query language, and then you have to fetch the database from the system itself. And sometimes you also have to scrape data from the websites, because let's say you're working on a problem where you're trying to predict the trends or the patterns which are emerging in the retail segment. So you need to fetch live data from the websites. So that is web scraping. So you probably develop a script which scrapes the data from the internet, and you structure the data in such a way that you feed it into the model. This part, data cleaning and pre-processing. So once you have the data and the problem in mind, you have to fetch the data. So you have to download the files, you have to call the APIs somehow, you have to download the files in some format which you need to format for the machine learning model. So after you have the data, you need to clean the data very accurately, because when you're trying to feed something into the machine learning model, there is a very famous saying which I think machine learning models do follow, is that if you put in garbage, you will get garbage out. So if you feed in inconsistencies, then you will get a model, even if you make the machine learning model extremely complicated, like extremely complex to gather patterns, if you feed in inconsistencies, it is going to output inconsistencies as well. So I read about somewhere that like most of the data scientists spend more than 70 to 80% of their time just cleaning the data and pre-processing the data. So these are the brief ways in which you can clean your data. So you obviously have to remove the duplicates and correct errors. So by correcting errors, I mean you have to, it is a contextual error thing. So if you have a column for ages, obviously ages cannot be negative. So you have to figure out some way to maybe change that into the correct form. Handling missing values, yes, the real world data set unfortunately has a lot of holes. It is not like a toy data set which is completely accurate. So if you talk about maybe a Google form or something as simple as a survey, there might be possibilities where the customers or whoever we're trying to target don't fill the data accurately. So you can't feed in missing values into the ML model because it will not perform the calculations properly. So you have to figure out some way how do you deal with missing values. So there are multiple techniques, there are complicated techniques as well, but it could be as simple as just dropping the observation itself. So if you have an age column missing, then you just drop the entire observation for that particular customer. You can also do imputations. So for example, if your data set is for the age between 30 to 40, so you can probably take the average of all the ages which are there in the data set and impute it with that part. So you also have to convert the types and check for consistencies because if you feed in something if you have a categorical column for country, let's say, and somewhere people have spelled out USA and somewhere they've said United States. So in your mind, you know that it's the same categorical variable and it will hold the same value. But you will have to fix that inconsistency and make it categorical, and you have to encode it in some form or the other. This is the splitting data is the most crucial part, and I think it will deserve its own call out. So essentially, have you guys heard about train test split by any chance? You guys have, right? So essentially, when you have the data ready after it's cleaned, after it's pre-processed, one part of pre-processing is to split the data set into at least two parts. So there is one more set which is called the validation set, but we can talk about that later. So you split the data into the training set and the testing set. Why do we do that? So the training set is essentially the data which you're going to feed into the model, through which it will learn what your outcome should be ideally. The testing set is left untouched. So by untouched, I again emphasize that it is not a part of the training process. So the very common split which we follow is 80-20. So 80% of the data we split it into training, which we'll use for the model to learn. 20% of the data is left aside, which is we'll touch that after the model has completely been trained, and we'll use to sort of evaluate how the model performs in the real world, because after all that's what will matter. For example, if you're trying to predict the churn, then all it matters is that the company should know which customer is probably going to stay or who's not going to stay in the future. So and there is also something called as validation set, which you use while fine tuning, but that is not the scope of the thing right now. You can change. Yeah, so once we have the clean data, we do data exploration and analysis, which is, and it is, I think, at least in my perspective, I enjoy doing this because you essentially use basic statistics, to just get a hold of what the data means. So and this is a very big part of what model would you choose, how would you train, and what would you like to predict. So the basic things which we do is we plot a distribution of all the variables which are there. So if you have age, you plot a distribution of ages, and you sort of figure out that okay, there are majority of the people who are there in the 30 plus age group, or so and so forth. You plot a box plot to understand if there are any anomalies in your data. If you're trying to predict for spend patterns, you will realize that a certain magnitude of people have spent enormous amount of money as compared to the others. So you will have to deal with those outliers very accurately, because they can really the skew distribution will not be a good representation of the accuracy of the model. So you'll have to decide if it is a data glitch or it is an actual anomaly. Then comes correlations and scatter plots. Have you guys heard of heat maps or correlation coefficients? So correlation coefficients, for those who don't know, is basically a coefficient which measures if one data point is increased, then what is the chance that the other variable will also increase with that correlation coefficient. So you essentially plot out the correlation coefficients and scatter plots between different types of variables and sort of understand which variable is essential for your model to feed in. And this also transitions to feature engineering, which people say that it goes very hand in hand with EDA, which is exploratory data analysis. So essentially features. So a data set will have two parts. One will be your features, which the model will use to train, and there will be a dependent variable which is dependent on the features. That is called the label. So for the example which I used before, the journey example, your features might look like the spending patterns, the customer success rate, and the target variable will just be a yes or no column, which will just say that if the customer has stayed or they have churned. So you have to make sure that your features are very accurate, because if you feed in the wrong features, if you feed in wrong features, the model is not going to be accurate in the real world. So you might have to create new features. You might have to select features out of the already existing features. You might have to transform features which will also improve the model performance. So let's say you have date of birth. Let's say you can easily translate that date of birth into age, which could be a really good predictor of your dependent variable. So these are some very basic examples of feature engineering. Can you go to the next slide? Yeah, this is the most interesting part, where actually ML comes into. And so once you have the data ready, once you know which features you want to feed into, you decide on which kind of model which you use to predict what you're trying to do. So there are multiple models where you can go by. So there is linear regression for predicting a regression task. There is decision trees, random forest, logistic regressions, etc. Neural networks for complex patterns. So you also need to explain the model's decisions. So you might prefer a simple model like a linear regression model for a simple data set for like predicting houses. But for a non-linear data set, if you have a lot of data, you might prefer a neural network per se. So after you've decided on which model you want to train, and the decisions are based on a variety of factors. So like I said, if you decide the nature of the data. If you see that the distributions in the EDA are sort of symmetric or linear per se, then you go with the linear regression model. If you think that you have a lot of data and if you observe some non-linear patterns in your data set, then you probably go with neural networks, because they're really good with dealing non-linear data. So once you decide the model, now it comes the real training part, where you actually feed the data into the model, and the model sort of recognizes the predictions and the outcomes which you're trying to predict by adjusting its parameters. So you train the model, and the model adjusts its parameter to reduce the training error. So let's say we're trying to predict house prices. So you have a column. That column will be fed into the model. The output will be stored, and it will be compared to what the model predicts. So according to what the model predicts, you will calculate an error. So the error is basically an estimation of how much your model is going off by, and essentially that gets back propagated, and you, through a loss function, you adjust the parameters over time. And it is an iterative process, so you can very much realize here that you've done something wrong in the previous processes and go back, fetch more data, and do the entire process again. Yeah. So once you've done this, the main thing which we need to answer is if our model is performing well on unseen data, which is a test set. So test set could be the split data which you have separated during the pre-processing part, or it could be just new data which you're trying to predict your problem statement for. So there are multiple metrics which we use to evaluate the performances. This is just for the purpose of examples. You guys can look over it later. I'll just go over the basic examples. So for linear regression, we have mean absolute error. So that is basically the mod and the square of the error between the outcome of the model and the real value. Then, yeah, so overfitting and underfitting, this is a very major problem in every machine learning model or in the entire realm of machine learning. Overfitting, have you guys heard of overfitting and underfitting? So overfitting is essentially that your model gets accustomed to the data set which you've trained in a very, what do you say, it's adhering to the patterns which are there in the data set, and when you try it with the real data set, it doesn't perform really well. Underfitting is just the opposite of it, that it fits the data which you're trying to feed very badly, and obviously there is a chance that it would also not recognize the patterns which are there in the real world as well. Okay, so there is. So now what we do is I have. Yeah. So this is a simple repository where we have a data set for sales prediction. So this is the TV, radio, newspaper sales, and it's the sales which we have gathered. So we'll sort of try to run. Sorry.
This is in Python?
Yes, this is all in Python.
Probably skip it.
So this is all the pre-processing part where you understand the shape of the data set, how many columns do they have. This is the info part where you see if the data types of the columns are accurate. So obviously this shouldn't be something else. This shouldn't be a string. If this is a string, you probably need to convert it into floating point number. This is the EDA part where you realize that what is the mean spend through TV, mean spend of radio, mean spend of newspaper, and so on and so forth. This is the cleaning part, and so basically we're checking for null values. If you remove, this is the part. If you use this code, it will probably give you the null values which are there in the data set. So in our data set, fortunately, we don't have any null values, so we don't need to remove anything or we don't need to impute anything as of now. Then we move to EDA, where we sort of understand the plots. So this plot is for the distribution of TV spend, this plot is for the newspaper, radio, and so on and so forth.
So with the newspaper plot, you can see outliers.
Correct.
These ones.
This is boxing newspaper.
Yes.
Yeah. This is again box plot. This is a scatter plot. So this is sales and TV. So you clearly realize through all of this is a scatter plot between the sales and all of the three variables which are there in the data set. So could you guys make a guess on what variable would be the best predictor or the strongest predictor of the sales out of these three scatter plots? Correct. So the first one, obviously, because it follows a linear relationship, which means that if the TV, if the spend on the TV advertising is more, the sales would rise. So you sort of realize that this might be a linear problem to solve. So you think of algorithms which use linear modeling instead. This is what I was talking about. This is a simple heat map. Heat map is nothing but a correlation matrix between all the variables which are there in the data set. So between TV and TV, obviously it will be a singular relationship. As you can see, as we saw in the plot itself, as Tanisha said, that rightly said that 0.9. So the relation between sales and the TV spend is the most. So we know that this variable might be a good indicator or a good predictor of the target variable. This is where we build the model. I have used Stats API for for building the linear regression model, but you guys can use scikit-learn, TensorFlow, any of those libraries. So this is the equation of a linear regression model, where you realize that here you realize that this is the predictor variable, which is sort of the most important thing in predicting the sales. So you choose that as a predictor. Yeah, perfect. So you split the data set into the features and the target. So this is the feature which we feed into the model. So let's say you feed in the average spend of the TV into the model, and it will try to predict that, it will try to give you the sales which you'll get through that. This is the splitting part where we use 7 and 3, so 70-30 split. 70% of the data is training data, 30% of the data is the testing data. So again, the training part is what will be fed into the model, the testing part is left untouched. So you train the linear regression model. We're not going to delve deeper into the technicalities of the model, but these are the results which you get. So one thing which you'll notice is this coefficient. So so this coefficient is basically, this is the constant, this is the coefficient. I don't know what it is. This one. Correct. So this is the outcome of the model. So this means that this much, if you increase the sales by 1 unit, this is the amount of increase which will happen in the sales. There are multiple valuation factors which will be discussed here as well. So yeah, this is the final model which we get, and as you can see, this is pretty accurate in predicting the scales. And one reason why we got a very accurate model like this is because we did all the processes above. If you went on to train the data on all the 3 parameters, you probably won't get an accurate result like this. Now we're going to evaluate the model, and by evaluating the model, we mean that we'll predict it on the test data. So the model doesn't know the labels of the test data. The model only knows the features. It will try to predict the feature target variable using the test data, and it will compare it with the real output which is there. So this is the prediction on the test set. This is the test set. So this is the prediction on the test set. Not bad. The model does pretty good on the test set as well. So you sort of understand that there is a higher probability that if you feed in unseen data to this model, it might be a bit accurate in predicting what the real pattern is or the real sales is. So do you have any questions? This is
Sure.
Yeah.
When you test the model,
Yeah.
it doesn't have any labels in it.
So
the
yeah,
model,
yeah.
the model like brings up the labels and figures out
Correct.
other existing labels.
Correct. That's right. So essentially, the training data, when you train the model has access to the labels itself, because that is how it will realize where it's going wrong, and it will try to adjust its weights. But once the model is trained, when you come to the evaluation part, there the model doesn't know the predictor variable of so essentially the Y test. So this is the labels of the testing data. This is the features of the testing data. So the model essentially only knows X test. So it only knows the features. It doesn't know what the labels are. It tries to predict the labels using the weights which you trained using the training data. And then it compares it with the real output, which is the Y test. And that is how the test error is calculated, and it sort of gives you an idea of how the model is performing on unseen data. Any more questions?
I'm still a little bit confused as to how EDA helps. You could give me an example because
Yeah, sure. Okay, go on.
like are you using defined outliers to clean or like
Okay, so EDA, exploratory data analysis. So the core concept of EDA is that your aim is to figure out correlations between the data. So if you weren't to do this, you don't have an idea, unless you can look at just numbers and figure out relations, you don't have an idea of what the data actually looks like. So exploratory data analysis just tells us, if we're just looking at it, you can see a strong correlation between X and Y here, whereas you can't see as much over there. So if you were to run the same model for this, just by looking at how the data is structured and how it's densely packed around the center, maybe you could predict a regression line like that. But yeah, the problem with that is it doesn't give you a outlier, or it doesn't give you a portrayal of the actual data set. Since the data is so scattered, you don't get a good relation between X and Y. So that makes sense. Any other questions?
Yeah.
So the data here, did you guys do the cleaning and the
Yes.
that
Where is that?
Oh, sure. So, I showed that before, but I will share this across after the workshop. But, so, the cleaning part is, the data is pretty clean here, but
Data set we use is fairly clean.
So there's no like missing points.
No, not for
there are
this
not.
data
So,
set.
we've tested that before.
But yeah, so he's yeah.
So here, so we've made sure that the data has no missing values.
Okay.
If there were any missing values, we would have to figure out a way to impute those values or sort of remove them. So for example, if this had a missing value, it might be, I don't know, make sense to replace or impute it with the average spend of the entire team.
So some solutions to missing values is either you remove the entire column,
Yeah.
or you put 0 or none. But it depends on the data.
It depends.
Yeah. For example, if your model runs on just integer values, you can't put none.
Yeah.
And if you put 0, it becomes an outlier. So the easiest solution is just remove that data. If you have enough data, that is. If you only have, let's say, 10 records, you don't have the option to remove data. So it's like, yeah, you have to compromise a little bit here and there. So data cleaning is pretty important. And we got lucky, we don't have a data set that is unclean. But if you look at real world data sets, you can just imagine data sets such as, okay, if you looked at COVID-19 data sets, if you had a form with people have to enter data, you'd realize that some records, even if when you fill forms, there will be a tendency of leaving things blank. Our problem is if that field was supposed to be an integer, and if we leave it blank, we can't, if you run it through a model, you can't process none as an integer. But if you put 0, because then 0 is also a value it can take. And so that's another issue that you have to take care of. So data cleaning comes down to just compromising on here and there as what you can get away with. And so
Any more questions before?
Where are you obtaining this data?
So this is a dataset from Cattle. I will provide you the link of the dataset. This can be downloaded from Cattle. So yeah, so this is the end of ML. Now we're sort of going to not deep dive, but a sort of brief overview about how
shallow dive into deep.
shallow dive. Yes. Yeah. So we're just going to delve deeper. So how many of you guys have heard about neural networks? None of you. Neural networks. So essentially, neural networks, all of the Gen AI which you see is basically trained on neural networks. It's a bunch of algorithms which a neural network has. So essentially, a neural network, the history of neural network is that as obvious as it sounds, it's inspired by the human brain. So if you guys have taken bio in high school, you will know that the neuron has a similar structure. It takes in dendrites, impulses through its inputs, and it sort of gives you an output in the form of So the perceptron is the basics of the neural networks. Like this is where the neural networks begin. The neural network is just essentially a combination of multiple millions of these perceptrons packed in together into different layers and getting output. So we're just going to I'm just going to demonstrate a simple flow of how a perceptron works. So you have a bunch of input values here. So your input values are essentially the features which we were talking about in previously. So each input has a weight which is assigned to itself. So let's say our input is probably age, and our probably output is a target variable where we're trying to predict the social media time someone is spending. So the age, the weight essentially gives you the importance of how much that feature age will play in deciding the output of your model. So essentially it's a function of x1, x2, x3, where your So this output, as you guys can see, it's just this output will just be this feature multiplied by this weight plus this feature multiplied by this weight plus this feature multiplied by this weight. So it will be x1 into w1 plus x2 w2 plus x3 w3, And so this doesn't end yet. This is the submission part. This is where we are right now. The most famous thing about the best thing about neural networks is that they're very good at catching patterns which are non-linear. So non-linear means that there is no particular way in which you can model the dataset. It could be any curve, or it could be any sort of shape which represents the data. So this is where activation functions come into picture. So activation functions, we're not going to delve deeper into them, but activation functions essentially ensure that you capture the non-linear patterns in your dataset as well. So this is the most common activation function which we use is a step function. So this is a binary classifier. So essentially, based on the submission, you decide if the submission is greater than 0.5, then you decide that the output is going to be 1. If the submission is less than 0.5, you decide that the output is going to be 0. And again, it is very contextual. It really depends on what problem you have to try to solve. This is a classification problem, but you might deal with regression problems as well. And essentially, you get output there. So this is forward propagation. This is how the model tries to predict. So you can relate it to how we use testing data to predict the labels on our dataset. Now, when we come to the training part, it is a bit complex and it is a bit calculus heavy. But just going over the brief parts of it. So essentially, when you get the output, so these weights are essentially randomized, or there are certain techniques which we can use to make sure that the weights are accurate according to the dataset. So, for example, by dividing it by the standard deviation of the dataset, etc. But essentially, you can assume that these weights are set to random values, not 0. These weights have to be fixed in such a way that it gives a right representation of the pattern which we're trying to predict in the dataset. So after these weights are set to be random, obviously, like it is nowhere possible that these weights are accurate and it represents the data properly. So after you do the forward propagation, you calculate the error, and error could be, for example, for a regression task, as I said, the error is just the square of the real term which the model which is predicted and the real term. So that is called MSE. Once you have the error, you plot the error function with the weights, and you sort of try to go to a place where the model weights have the lowest value of loss. I don't know if it makes sense. So you calculate the derivatives, go in the backward direction and adjust the derivatives, adjust the weights in such a way that your model is deviating to the point where the loss is the lowest. We have a short playground. So this is a website which you guys can visit. This is a very famous library, TensorFlow, which has Python implementation of neural networks. So this is 2 variables, so 2 inputs, 1 neuron and 1 output. We have a toy data set where we have a classification problem. So this is a classification problem where one class is blue and one class is orange. So we try to run the neural network here. Epochs is basically the number of iterations which will take. So we start the model. So as you can see that, so this was very quick. So as you can see that this is what the model is predicted as the divider. That this is the division between the orange class and the blue class. And the activation function we've used is sigmoid because this is a regression problem, so we have to stick with something else. But that is about it. I'll be happy to delve deeper if you guys are interested, and we're going to probably follow this up with more workshops. Rohan had an idea about a workshop.
So, first let me just summarize what we've talked about in the past hour. I know it's been a little heavy. I hope so. What you can do is, if you're interested in neural networks, 3 Blue 1 Brown. He's a YouTuber who has a very good series on neural networks, very well animated. 3 Blue 1 Brown. 3 Blue 1 Brown. So it's a very good YouTube series talking about neural networks. He talks about machine learning, AI. It's very, very graphic, very well made. He's also the author of a Python library called Manin. So let's just go over everything. We talked about the introduction to ML, machine learning, AI, the neural networks is towards the end. And we talked about the process of how a machine learning task is done, or a script is written, or what the steps you take to test and train data sets or data to get what you require or desired output. Now, another workshop for the future workshop, what we have planned. If you have any ideas, you can shoot. But what we're currently thinking of is diving deeper into AI. So today we talked about machine learning. Let's talk about AI next. And something that I found very interesting with AI, which I would like to, which you guys can have suggestions as well, is the rise of DeepSeek. Has anybody heard of DeepSeek? So, very interesting how DeepSeek is beating GPTs and other models with such a low budget. So, and also we can talk about different aspects such as distilled models, and what distilling has to do with the current whatever, not politics, but what's going on in the world right now with the AI and language processing. So, any other questions? Okay. So we'll end the session here. Thank you for your time.
If you have any suggestions of what the next workshop